Time has traditionally been understood as the carrier of physical persistence. If, however, physical persistence is instead understood as an evolving organizational phenomenon, then the role of the carrier becomes available to be fulfilled by something else. Persistence is understood here as the continued existence of organization despite continual structural change, while a carrier fulfills the role through which that persistence is realized. In biology, the genome fulfills this role by carrying hereditary organization across successive generations despite continual structural change. Biology therefore demonstrates that persistence can be understood in terms of a carrier. The same question may therefore be asked of physics. If physical persistence likewise requires a carrier, what fulfills that role? To investigate that question, it is natural to ask whether the geometric frameworks already used to describe the physical universe contain the organizational structure capable of fulfilling that role. General relativity restricts the geometry to a torsion-free affine connection. Standard Einstein-Cartan theory relaxes this restriction by admitting torsion, although torsion remains non-propagating. Non-minimal Einstein-Cartan theory further relaxes the dynamical restriction by allowing torsion to propagate. Poincaré gauge theory further relaxes the geometric restriction by permitting torsion through contorsion to modify the affine connection and thereby participate alongside curvature in the physical geometry. This leaves open the interpretation of torsion itself, whether it merely reformulates curvature or constitutes a second independent geometric degree of freedom. The framework proposed here is not primarily concerned with whether torsion reformulates curvature or constitutes a second independent geometric degree of freedom. Rather, it explores whether their integration within a modified affine connection constitutes an evolving geometric organization that fulfills the role of the physical carrier through which physical persistence is realized. Having identified the proposed ontology, the next question is not how it should be parameterized, but what the ontology itself requires. The framework is committed to the existence of an evolving geometric carrier through which physical persistence is realized. It is not, however, committed to any particular ordering parameter. Whether physical succession is represented by one ordering parameter, several or none at all, does not alter the underlying ontology, provided the evolving organization of the carrier remains well defined. The framework therefore proceeds on the assumption that physical succession can be represented entirely through the evolving relationships within the carrier without requiring an independent ordering parameter. On this interpretation, the framework does not require time as a fundamental ontological entity. This should not be taken as a claim that time does not exist, but rather that the framework itself does not depend upon time as a fundamental ontological entity. Whether time nevertheless exists independently lies beyond the scope of the present framework. The framework begins with a three-dimensional manifold, which provides the underlying geometric structure through which physical persistence is realized. Consistent with the framework's treatment of the carrier as an evolving three-dimensional geometry rather than a four-dimensional spacetime, the manifold is equipped with a Riemannian metric, providing the notions of distance, angle, and volume appropriate to a purely spatial geometry. Together with a Riemann-Cartan connection, this constitutes a Riemann-Cartan geometry on the manifold, allowing the geometry to support both curvature and torsion. Within this geometric setting, the framework adopts the Riemann-Cartan connection as a generalization of the torsion-free Levi-Civita connection associated with the Riemannian metric. The Levi-Civita connection is the unique metric-compatible affine connection that contains no torsion and therefore serves as the natural geometric baseline from which the more general connection is constructed. The transition from the Levi-Civita connection to the Riemann-Cartan connection is achieved through the introduction of contorsion. Rather than replacing the affine connection, contorsion modifies the torsion-free Levi-Civita connection to produce the more general Riemann-Cartan, or modified affine connection, while preserving metric compatibility. Within this formulation, contorsion encodes the contribution of torsion to the affine connection. Torsion is therefore not introduced as an independent geometric object, but as a property of the modified affine connection itself. This allows both curvature and torsion to participate in the integrated geometric carrier of the manifold that underlies physical persistence. Having established the geometry of the carrier, we can now consider its possible geometric configurations. Each configuration represents a particular state of the integrated geometric carrier, described by the Riemannian metric together with the associated Riemann-Cartan connection and its resulting curvature and torsion. The collection of all admissible geometric configurations constitutes the carrier's configuration space. The evolution of the carrier may then be understood as a trajectory through this configuration space. Rather than evolving through a four-dimensional spacetime, the carrier progresses through successive geometric configurations ordered by the framework's ordering parameter. This trajectory describes the evolution of the carrier's integrated geometric organization, providing the foundation upon which its dynamics can be formulated. The framework further proposes that this evolution is history-dependent. Successive configurations are not determined solely by the carrier's present geometric state, but also by aspects of its preceding geometric evolution. In this way, the carrier retains a geometric dependence upon its evolutionary history, introducing a form of geometric hysteresis into its dynamics. This history dependence motivates the formulation of a history-dependent geometric evolution law, describing how the integrated geometric carrier progresses through configuration space. The evolution of the carrier depends upon the geometric history of its present organization. This principle proposes that the carrier's evolution is determined not solely by its present geometric configuration, but also by the geometric history embodied within that configuration. In this way, the carrier retains a history-dependent geometric organization as it progresses through configuration space, providing the conceptual foundation for geometric hysteresis. The evolution law therefore establishes the fundamental dynamical principle of the framework, motivating consideration of the established mathematical formalisms within which that principle might eventually be expressed and the proposed dynamics formulated. The Lagrangian and Hamiltonian formalisms provide the natural mathematical frameworks within which the history-dependent geometric evolution law might eventually be expressed and the proposed dynamics formulated. Because the framework remains at a conceptual stage, they are presented not as definitive mathematical formulations of the proposed dynamics, but as established mathematical frameworks through which such formulations could ultimately be developed and tested. Rather than introducing new dynamical principles, these formalisms provide established mathematical means by which the history-dependent evolution of the integrated geometric carrier could be formulated. The Lagrangian formalism provides a natural variational framework through which the proposed evolution law could be expressed. By describing the carrier's evolution through a variational principle, it offers a systematic means by which the consequences of the history-dependent geometric evolution law may be developed mathematically. In this context, the Lagrangian is not introduced as a new physical principle, but as a possible mathematical expression of the governing law already established. The Hamiltonian formalism provides an equivalent canonical framework describing the same proposed dynamics from a complementary perspective. Rather than replacing the Lagrangian description, it reformulates the same history-dependent evolution in terms of the carrier's evolving geometric state and the quantities governing its subsequent evolution. As with the Lagrangian formalism, its role is not to introduce an alternative physical interpretation, but to provide a complementary mathematical framework through which the implications of the proposed evolution law may be explored. Together, the Lagrangian and Hamiltonian formalisms represent complementary mathematical approaches to the further development of the framework. Their inclusion identifies the natural mathematical direction suggested by the proposed ontology without claiming a complete or empirically validated formulation of the underlying dynamics. Instead, they outline how the history-dependent geometric evolution law could be expressed mathematically, should the framework prove to provide a useful description of physical reality.